A spacecraft can voyage through the cosmos without a single drop of fuel. This is the promise of solar sailing, a real technology that harnesses the gentle, relentless push of sunlight. For centuries, our reach into space has been shackled by the immense weight and cost of rocket propellant. But solar sails offer a way to slip those chains, enabling journeys that are endless, silent, and free. By the end of this exploration, you will see how this elegant idea could completely reshape humanity's future among the stars. We will uncover how a sheet thinner than a hair can catch light, and how missions already underway are testing sails that could one day race to another sun. What does it feel like to ride a sunbeam into the great unknown? The force that propels a solar sail is both subtle and profound. Light, for all its ethereal nature, carries a real physical punch. Each particle of light, a photon, possesses momentum despite having no mass of its own. When these countless photons from the sun bounce off the sail's mirror-like surface, they transfer their momentum to it, giving the spacecraft a gentle, continuous push. This is not the forceful shove of wind against a canvas, but rather a persistent, silent nudge from a river of light. The idea captivated brilliant minds for centuries, from Johannes Kepler, who observed comet tails being blown by a celestial breeze, to James Clerk Maxwell, who mathematically proved that light exerts pressure. This radiation pressure, the force from electromagnetic waves, is the engine. On Earth, its effect is utterly negligible, akin to the weight of a single sheet of paper resting on your palm. But in the pure vacuum of space, where there is no friction or air resistance to slow things down, that whisper of a force never stops. Day after day, week after week, the acceleration builds. It is the ultimate tortoise in a cosmic race, starting imperceptibly slow but eventually reaching speeds no conventional rocket could ever sustain. Expert physicist Neil deGrasse Tyson often highlights the sheer elegance of this, how solar sailing turns a fundamental property of the universe into a limitless engine. The genius is in harvesting this constant push, allowing a craft to spiral out from Earth on a rising tide of sunlight, moving faster and faster over time. But how do you build a vessel to catch such a delicate breeze? This challenge leads us directly to the intricate engineering of the sail itself. Building a vessel to catch light means creating a sail that is both vast and almost impossibly delicate. The material itself is the first engineering marvel, a gossamer thin membrane that must be incredibly lightweight, highly reflective, and strong enough to survive the brutal environment of space. Modern sails are often crafted from advanced plastics like mylar or a polyamide film called Captain. These materials are then frequently coated with an ultra-thin layer of aluminum, turning the sail into a giant, mirror-like sheet designed to bounce photons back with maximum efficiency. The entire objective is to maximize the surface area that catches the light while minimizing the mass that must be pushed. Some experimental sails are just a few microns thick, far thinner than a single human hair. Imagine the challenge of engineering something so fragile yet so vast, a structure that could cover a football field but weighs little more than a small bag of sugar. But mere thinness is not enough. This enormous, delicate sheet must endure the extreme conditions of space, from the searing heat of direct sunlight to the deep freeze of shadow, all while resisting a constant peppering of micrometeoroids and intense radiation. The sail cannot simply be a single flimsy sheet. It is an intricate structure typically divided into 4 triangular quadrants, much like a giant kite. These sections are supported by long, lightweight booms that unfurl from a central box, the spacecraft bus. These booms are engineering triumphs in their own right, often made from carbon fiber composites or clever shape memory alloys. These alloys can be packed into a tiny volume for launch, and then, when heated by the sun, they smoothly twist back into their intended, rigid form, pulling the sail taut. The deployment of this entire system is a nail-biting ballet in the void. One of the most brilliant demonstrations came from the Japanese Space Agency's IKAROS mission. It used centrifugal force, spinning the entire spacecraft to fling its sail out into a perfect square. That delicate, unfurling dance is one of the most critical and risky moments in any solar sail mission. A single snag could mean failure, but once that vast, mirror-like wing is successfully opened to the sun, a new and equally fascinating challenge begins. How do you steer a ship that has no rudder and is pushed by an invisible force? Steering a vessel with no rudder and an invisible wind demands a new kind of seamanship. Without thrusters to fire for a quick burst of correction, pilots of a solar sail must think like ancient mariners on a cosmic ocean. The only way to change course is to adjust the sail's angle, its attitude relative to the sun. A perfectly perpendicular sail catches the full force of the light, pushing it directly away from our star, but tilt that vast mirror just a few degrees and the pressure vector shifts. Photons bounce off at an angle, pushing the craft sideways as well as forward. This allows the sail to perform a maneuver called tacking, much like a sailboat zigzagging against the wind. By carefully controlling this angle over time, a solar sail can spiral outward from the sun or even inward, navigating the gravitational currents of the solar system on a river of light. But how do you tilt a structure as large as a building with the precision of a watchmaker? The answer lies inside the central spacecraft bus. Small, spinning devices called reaction wheels are the hidden muscle. By speeding up or slowing down these internal flywheels, the entire craft slowly rotates in the opposite direction, minutely adjusting the sail's pitch and yaw without expending a single drop of fuel. Some future concepts are even more elegant, envisioning sails with panels that can change their reflectivity. Imagine making one side of the sail a brighter mirror than the other. The more reflective side would experience a stronger push from sunlight, naturally causing the entire structure to twist and turn. This method of navigation requires a complete paradigm shift in mission planning. Trajectories are not simple arcs from point A to point B. They are complex, beautiful spirals calculated to ride the constant pressure of sunlight, a dance with physics that can take months or years. The Planetary Society's LightSail 2 mission provided a spectacular proof of this principle in action. From Earth orbit, this small craft repeatedly angled its sail to catch the sunlight, raising its altitude by hundreds of meters using nothing but the power of photons. It was a stunning demonstration of controlled flight by light. This mastery of celestial sailing, of turning sunlight into a precise navigational tool, is what truly unlocks the solar system. But this modern achievement rests on the shoulders of visionary thinkers who dared to believe in such a possibility centuries ago. The dream of a functional solar sail spent decades trapped in theory and laboratory experiments. Then, in 2005, a small spacecraft named Cosmos 1 aimed to make history. Built by the Planetary Society, an organization funded not by governments but by thousands of public supporters, it represented a collective leap of faith. Its mission ended tragically when the rocket failed, but the ambition itself was a crucial spark. The true breakthrough arrived just 5 years later, far from Earth. Japan's IKAROS spacecraft, a technological marvel, became the first to successfully deploy a solar sail in the void between planets. That 14-meter square membrane, thinner than a human hair, unfurled perfectly on its journey to Venus. It was not just a passive mirror. IKAROS proved it could feel the gentle pressure of sunlight, measuring the acceleration and even using that pressure to steer. This was the moment solar sailing transformed from a beautiful hypothesis into a working engine. Back in Earth orbit, a series of smaller missions cemented the proof. NASA NanoSail D2 deployed its own compact sail, and then the Planetary Society, undeterred by its earlier loss, launched LightSail 1 and 2. LightSail 2, in particular, became a crowning public achievement. For years, this breadbox-sized craft used its delicate postage stamp-sized sail to perform controlled maneuvers, repeatedly raising its orbit around our planet using nothing but the power of photons. These were not just scientific experiments. They were the first successful voyages of a new kind of ship, providing the hard data that silenced decades of skepticism. The fundamental principle was no longer in question. With the basic mechanics of sailing by light firmly established, the visionaries and engineers could finally lift their gaze from Earth orbit to the stars themselves. The very next missions are already built and waiting for their ride to the sky. NASA NEA Scout is a tiny pioneer, a spacecraft no larger than a shoebox that will hitch a ride aboard the powerful Artemis rocket. Once released into the void, it will unfurl a vast silver sail, over 86 square meters in area, and begin a remarkable journey. Its destination is a near-Earth asteroid, a small, ancient rock drifting through the black. Using only the pressure of sunlight, this miniature scout will maneuver around the asteroid, capturing high-resolution images and gathering data. This mission demonstrates the perfect utility of a solar sail. For a small, low-cost spacecraft, it provides the gentle, continuous propulsion needed to explore these miniature worlds, a capability once reserved for much larger, more expensive probes with conventional engines. But the ambition does not stop there. On the drawing board is an even grander vessel, the Solar Cruiser. Its proposed sail would be a colossal 1,700 square meters, a shimmering expanse the size of a city apartment block. This giant would not voyage to distant planets. Instead, it would perform a delicate balancing act, using its sail to hover at a unique gravitational point between the Earth and the Sun. From that perfect vantage, it would act as an advanced warning system, monitoring the Sun's violent outbursts and giving us crucial time to protect our power grids and satellites from solar storms. These two missions represent a monumental leap. They are no longer simple experiments to prove the sail works. They are practical tools, scaling up the technology to perform real, vital jobs in space. They will test next-generation materials that are lighter and stronger, flawless deployment systems for sails larger than any before, and sophisticated software that can pilot these giant, silent ships with perfect precision. This is the bridge from a brilliant concept to a foundational technology for exploring our solar system. And once we have mastered sailing in the inner system, a far grander ocean awaits our attention, out where the sunlight grows faint and the giant planets drift in the cold. The sunlight grows faint beyond the asteroid belt, but the reach of a solar sail does not have to end there. For voyages to the distant, ice-shrouded giants, engineers are designing sails that bring their own sun. The concept is called laser sailing, and it transforms the entire idea. Instead of relying on the sun's diffuse light, a giant laser array, either on Earth or in orbit, would focus a relentless, concentrated beam of photons onto a sail. This directed energy push could continue for days or even weeks, accelerating a lightweight sailcraft to a staggering fraction of light speed. Think about the journey to Jupiter. A conventional mission takes years, but a laser-boosted sail could make the same trip in a matter of months. This speed opens up entirely new possibilities for exploration. We could send rapid reconnaissance missions to the fascinating icy moons of the outer solar system, worlds like Europa and Enceladus, which hide vast subsurface oceans beneath their frozen crusts. A nimble sailcraft could enter orbit around these moons, using its gentle, fuel-free propulsion to maneuver into perfect positions to search for signs of alien life. But it could do more than just visit moons. A solar sail could also act as a unique mobile observatory. It could perform a maneuver impossible for any other spacecraft, using light pressure to hover at a high inclination over the poles of Jupiter, studying its immense and violent magnetosphere from angles we have never before seen. This laser-boosted method turns the solar sail from a slow and steady tortoise into a veritable speed demon for the outer reaches. And once you have a technology that can be pushed to such incredible velocities by a focused beam of light, your gaze is inevitably drawn beyond the edge of our own solar system, to the pinpricks of light in the profound darkness between the stars. Reaching for another star demands a leap in scale that is almost incomprehensible. The Breakthrough Starshot initiative embodies this audacious dream, aiming not for a planet but for a sun. Its target is the Alpha Centauri system, our closest stellar neighbor, a trio of suns located over 4 light-years away. For a conventional spacecraft, that journey would take tens of thousands of years. Starshot's solution is to turn solar sailing on its head. Instead of relying on our sun's gentle, diffuse light, the plan is to build a colossal laser array on Earth, a phalanx of beams combining into a single, focused river of light with the power of a gigawatt. This concentrated energy would be trained on a fleet of tiny probes, each no heavier than a gram, equipped with a LightSail only a few meters across. The push from this terrestrial star would be anything but gentle. In mere minutes, these nanocraft would be accelerated to a staggering fraction of light speed, over 20%. At that velocity, the journey to Alpha Centauri would take just over 20 years. Imagine that, within a single human generation, we could receive images from another star. But the engineering hurdles are as immense as the ambition. How do you design a sail that can withstand an acceleration so violent it would tear ordinary materials to shreds? The sail would need to be almost perfectly reflective because any energy it absorbs from that powerful laser would instantly turn to heat, vaporizing the craft in a flash. Researchers are investigating miraculous new substances called metamaterials, engineered with structures smaller than the wavelength of light, designed to reflect nearly every single photon. The entire probe, with its cameras, sensors, and transmitters, must be miniaturized to the size of a postage stamp, a feat of nanotechnology that pushes the very boundaries of modern physics. Starshot is more than a single mission plan. It is a forcing function for global innovation, compelling us to solve problems in material science, optics, and communications that we have never before faced. It proves that the principles of solar sailing, once seen as a method for slow, stately travel, could actually be the key to the fastest voyages ever conceived. This vision transforms the sail from a simple solar catcher into a cosmic surfboard, designed to ride a wave of our own creation. It redefines the possible, suggesting that the first human-made object to reach another star may not be a mighty rocket, but a silent, shimmering sail. This silent, fuel-free nature makes solar sails perfect scientific observatories. They can carry sensitive instruments to places other spacecraft can barely reach and hold them there for years without disturbance. Imagine a mission to study the sun. Conventional probes whip around it, their views fleeting. A solar sail, however, could perform a seemingly impossible maneuver. It could use the pressure of sunlight to balance against the sun's gravity, allowing it to hover high over one of the solar poles. We have never stared directly down at the sun's poles for a long period. That perspective is the missing key to understanding the sun's 11-year cycle of activity. By watching the complex magnetic fields churn at the poles, a solar sail observatory could finally unravel the mysteries of the solar wind and help us predict the solar storms that threaten our technology on Earth. For studying planets, sails offer a different kind of magic. Instead of sending one large, expensive orbiter, we could deploy a fleet of dozens of small, identical sailcraft. Think of them as a swarm of scientific drones. Released around Mars or Jupiter, they could spread out, each one using its sail to hold a unique position. One could skim the upper atmosphere, while another monitors the magnetosphere's boundary, and a third looks on from a distance. Together, they would build a dynamic, three-dimensional model of the planet's environment in real time, watching how it breathes and changes. This is like going from a single photograph to a full-length movie, revealing the intricate dance between a world and the space that surrounds it. Their longevity is another superpower. A sailcraft could station itself as a permanent sentinel, monitoring space weather for decades, or tirelessly scanning the skies for asteroids that might one day wander too close to Earth. As astrophysicist Avi Loeb suggests, solar sails could be the trucks of the solar system, delivering sensors to every corner on a shoestring budget. The data they gather could fundamentally reshape our knowledge of how planets form and how our star governs its domain. This incredible versatility stands in stark contrast to the technology that has carried us into space for the last 70 years. Think of a conventional rocket as a sprinter. It explodes off the starting line with breathtaking power, muscles burning fuel in a spectacular, short-lived burst to break free of Earth's gravity. But once in the vacuum, that sprinter is out of breath, coasting on momentum. This is the tyranny of the Tsiolkovsky rocket equation, a fundamental law of astronautics. It dictates that the faster you want to go, the more propellant you need. But that propellant itself has mass, requiring even more fuel to push that mass, creating a vicious cycle where the vast majority of a rocket's launch weight is just the stuff it burns to move. It is a system of diminishing returns, ultimately limiting how far and how fast we can travel. Electric propulsion, like the ion thrusters used on many deep space probes, is the marathon runner. It is incredibly efficient, providing a gentle but continuous thrust for months or even years by ejecting tiny charged particles. Yet even this efficient runner needs to carry a lunchbox. It requires a finite supply of propellant like xenon gas, which will eventually run out, ending the mission. The ion engine also needs large solar panels to power it, adding mass and complexity. Now place the solar sail in this race. It is neither sprinter nor marathon runner. It is the sailor who has learned to read the wind. Its engine has no moving parts and never runs out of fuel. The sunlight that pushes it is free and limitless. This gives the solar sail a theoretical superpower that makes rocket scientists take notice, something called unlimited delta V. Delta V, or change in velocity, is the currency of space travel. It measures a spacecraft's ability to change its speed and direction. For a rocket, delta V is a finite tank of gas you burn through. For a solar sail, it is an infinite account. As long as you remain in the light, you can spiral, change orbits, and accelerate for decades, all without a single refill. The trade-off is patience. The thrust from sunlight is whisper-thin. A sail will never win a race from Earth to the moon against a chemical rocket. but for a journey to a distant asteroid or to station keep for years near the Sun, the sail's persistent nudge wins over time. It starts slow, but it never, ever stops pushing. Over a span of years, that constant acceleration can build up to speeds far greater than any chemical rocket could ever sustain, because the rocket would have run out of fuel long ago. This fundamental difference reshapes how we design missions. We are no longer constrained by the mass of the fuel we can carry, but by our ingenuity in harnessing the environment. We shift from the explosive power of chemistry to the graceful, eternal push of physics itself. This ability to defy gravity's pull with a nudge of light unlocks orbits that were once pure fantasy. Imagine a spacecraft not circling the Sun, but hovering beside it, holding a perfect, stationary vigil over a single solar feature. This is a displaced orbit, a configuration made possible only by the constant, gentle pressure of a solar sail. By angling its vast mirror to push against a fraction of the Sun's immense gravity, the sail can balance the craft in a position that is not a natural Lagrange point. It creates its own stable vantage point. For solar scientists, this is a revolutionary tool. Instead of watching the Sun from an orbiting platform that periodically swings behind the Earth, a solar sail observatory could maintain an uninterrupted stare, monitoring the development of sunspots or the eruption of a solar flare in real time for years on end. The same principle applies closer to home. Consider the challenge of observing Earth's polar regions. Traditional satellites in geostationary orbit are too far away to see the poles clearly, while lower orbits constantly swing the spacecraft away from the area. A solar sail could solve this. It could maintain a unique, non-Keplerian orbit, using light pressure to constantly adjust its path and hold a position that provides persistent, high-latitude coverage. This would give us a never-ending live stream of the Arctic and Antarctic, transforming our understanding of climate change, ice melt, and polar weather patterns. This capability for active station keeping without a single drop of propellant is what makes the solar sail more than just a transport vehicle. It becomes a permanent sentinel. We could deploy fleets of these craft as enduring communication relays at strategic points between Earth and Mars, or as permanent weather monitors that watch for solar storms, giving our power grids and satellites precious extra hours of warning. The sail transitions from a simple engine to a dynamic platform, a piece of permanent space infrastructure that pays for itself through longevity. This radical shift in what is possible in orbit also brings with it a compelling economic case, one that could make space far more accessible than it is today. The true revolution of solar sailing may be measured not in velocity, but in dollars and cents. By completely eliminating the need for onboard propellant, a solar sail slashes the single greatest constraint on any mission, its launch mass. Every single kilogram sent to orbit carries a staggering price tag, often tens of thousands of dollars. A conventional spacecraft is mostly a flying fuel tank, but a sailcraft is pure payload and platform, a featherweight explorer. This dramatic weight reduction completely changes the launch calculus. A mission that once demanded a dedicated, powerful, and exorbitantly expensive rocket could now hitch a ride as a secondary payload on a much smaller, cheaper vehicle. It is the difference between chartering a private jet and sharing a bus ticket into space. Once operational, the economic benefits compound. With no fuel to run out and an engine made of light, the spacecraft's lifetime is no longer measured by its propellant tank. Its mission ends only when the harsh space environment finally degrades its components, a process that could take decades. Imagine a single scientific probe studying the Sun for 20 years, continuously gathering data for a one-time launch investment. The return on that investment becomes immense, turning each mission into a long-term observatory. This radical cost-effectiveness is a powerful democratizing force. It suddenly places deep space exploration within the financial reach of university laboratories, smaller countries with burgeoning space programs, and innovative private companies. As launch providers like SpaceX continue to drive down the cost of access to space, their progress creates a perfect synergy with these ultra-efficient sailcraft. We are approaching a tipping point where launching a fleet of small, intelligent solar sails could cost less than a single traditional planetary mission. This is the blueprint for a new golden age of robotic exploration, one defined by proliferation and constant presence. It transforms our vision of the solar system from a collection of distant, rarely visited points into a networked domain humming with activity. But to weave that web, we must first learn to build sails on a truly monumental scale. The journey from a proof of concept to a practical tool is measured in square meters. We have already mastered the art of the small with sails like LightSail 2, no bigger than a boxing ring. The next leap requires building giants for missions that will ride sunlight to the asteroid belt or hover near the sun. Engineers are designing sails that span the area of a city block, thousands of square meters of shimmering film. Deploying something so vast and delicate in the weightlessness of space is a ballet of physics and precision. One leading concept involves booms that uncoil like massive, ultra-light tape measures, slowly pulling the sail taut as they extend. Another idea uses inflatable tubes that stiffen permanently when exposed to the deep cold of shadow, creating a rigid frame without a single heavy strut. The truly audacious designs intended for interstellar travel abandon booms entirely. They are spin-stabilized, using the centrifugal force from the craft's own rotation to fling the sail into a perfect, flat disk, a shimmering carousel spinning through the void. This dance of deployment is one of the most critical moments. A single wrinkle or a snagged cable could render the entire sail useless. Every increase in scale introduces new complexities, a delicate interplay of forces where the gentle pressure of sunlight must be balanced against the sail's own vibrations and the subtle tug of gravity. Yet, with each new square meter, new capabilities are unlocked. A sail the size of a square kilometer, a vast silver sea floating in space, could be used for planetary defense. By flying in formation with a hazardous asteroid for years, its subtle photon push could gradually nudge the rock onto a safer trajectory, using the softest of touches to avert a catastrophe. The materials themselves must evolve to meet this scale. For the immense sails of the future, researchers are turning to miracles of modern science like graphene, a lattice of carbon just one atom thick, yet stronger than steel. Or ultra-thin membranes of silicon nitride, engineered to reflect nearly every photon from a powerful laser beam without melting. Building bigger is not just about making a larger sheet. It is about weaving a smarter fabric, one that can be steered with patches that change reflectivity or even repaired by swarms of tiny robots. The path forward is clear. We must learn to build not just sails but silent, soaring cathedrals of light. Such a delicate dance with sunlight demands a mind of its own. The complex, dynamic nature of solar sailing makes it a perfect partner for advanced artificial intelligence. An onboard AI pilot could transform the sail from a simple craft into a thinking explorer. Instead of following a rigid, pre-programmed path from Earth, this intelligent system would constantly analyze its environment. It would feel the subtle ebb and flow of solar pressure, measure the gravitational tugs from nearby planets, and then autonomously tweak the sail's angle for perfect efficiency. You would not need to command every minor course correction. You could simply give the sailcraft a goal, like intercept that comet or maintain this viewing angle of Jupiter, and the AI would figure out the most elegant sailing strategy on its own. This is like the difference between remotely steering a drone with a joystick and telling a seasoned captain to sail west. The captain uses their intuition and experience to read the waves and wind, making countless tiny adjustments you would never think to command. The AI becomes that seasoned captain for the cosmic ocean. It could even learn from its journey. Machine learning algorithms could digest streams of sensor data, learning to predict the sun's violent outbursts. Before a coronal mass ejection even arrived, the AI could already be tilting the sail to minimize stress on its delicate structure or to catch the resulting wave of heightened solar pressure for an extra boost. This level of autonomy is not just a convenience. For missions venturing to the outer solar system, it is an absolute necessity. The communication delay with Earth grows to hours. You cannot joystick a spacecraft around an obstacle when the signal takes 45 minutes to reach it. The craft must be able to think for itself, to react to surprises in real time. This intelligence becomes even more powerful when you think not of one sail, but of many. Imagine a swarm of these smart sailcraft, a flock of silver wings journeying together. Their onboard AIs could communicate, enabling collaborative behaviors no single probe could manage. They could spread out to act as a giant, distributed sensor array, creating a three-dimensional map of a planet's magnetosphere. Or they could perform coordinated maneuvers, using their combined light pressure to gently nudge a small asteroid. The marriage of artificial intelligence with solar sailing creates a new kind of entity, a truly adaptive and intelligent explorer capable of navigating the profound challenges that await in the deep, dark space between the stars. Yet this elegant engine has its own unique constraints. The fundamental challenge of solar sailing is its incredibly gentle touch. The thrust-to-mass ratio is minuscule, meaning the initial push from sunlight feels like the weight of a single coin resting on your palm. This continuous acceleration is the sail's greatest strength, but it demands immense patience. A mission to another planet would begin with a slow, graceful spiral away from Earth, taking months to build up the speed that a chemical rocket achieves in minutes. This makes solar sails ill-suited for urgent missions or any trajectory that requires a sudden, powerful change in velocity. For now, the solar sail is a long-distance voyager, not a sprinter. Its delicate physical form presents another vulnerability. That vast, gossamer-thin membrane is perpetually exposed to the hazards of space. A single impact from a micrometeoroid, smaller than a speck of dust but traveling at cosmic velocities, can tear a hole right through the sail. Over years, the relentless barrage of ultraviolet radiation from the sun slowly degrades the sail's mirror-like coating, reducing its ability to reflect photons and sapping its power. Navigating this vessel is a masterclass in orbital mechanics. Unlike a rocket that coasts for most of its journey, a sail is constantly under acceleration. Mission planners must account for this never-ending push, calculating its complex interplay with the gravitational pulls of the sun, planets, and moons. The slightest miscalculation in the sail's angle can compound over time, sending the craft far off course, and the sail's power source itself has a finite range. As a craft journeys toward the outer solar system, the sunlight grows faint. The pressure it exerts weakens with the square of the distance, meaning that at Jupiter, the push is only about 1/25th of what it was near Earth. By the time you reach Saturn, the pressure is almost negligible, a mere whisper against the sail. These limitations are not failures of the concept, but rather the natural boundaries of its design. They define the mission envelope, showing us where solar sails truly excel and where other technologies must take over. But the human drive to innovate is never satisfied with boundaries. These very challenges are the puzzles that are inspiring a new generation of engineers to build even better sails. While the solar sail catches light, other concepts aim to ride a different kind of cosmic wind. The solar wind, a constant stream of charged particles flowing from the sun, offers its own powerful current. To harness it, we look to the electric sail or e-sail. Conceived by scientist Pekka Janhanen, this is a vessel without a sailcloth. Imagine instead a spiderweb of long, slender wires, perhaps 20 kilometers in length, extending from a central hub. These tethers are given a strong positive charge. When the solar wind, which is full of positively charged protons, flows past, the like charges repel. Each proton pushes gently against the charged wires, and that collective push translates into a steady, propellant-free thrust. Its genius lies in its resilience. In the outer solar system, where sunlight grows weak, the solar wind remains a relatively constant river, making the e-sail a potentially more effective engine for the realm of the giant planets. Then there is its cousin, the magnetic sail or mag sail. This concept envisions a gigantic loop of superconducting wire. When electrified, this loop creates an immense magnetic field, a kind of invisible magnetic bubble stretching for kilometers around the spacecraft. As the charged particles of the solar wind encounter this magnetic shield, they are deflected, pushing against the field and nudging the craft forward. It is like a force field being used as a sail. Each of these systems has its own ideal mission. A heavy cargo ship, slowly transporting supplies between Mars and the asteroid belt, might rely on the robust, steady push of an e-sail. Meanwhile, an ultralight probe like the breakthrough Starshot craft would achieve its incredible speeds only with the focused power of a laser on a traditional LightSail. The future of cosmic sailing is not a single technology, but a versatile portfolio. We are building a toolkit for the stars, with each tool designed for a specific purpose. This global vision of sailing the solar system is not confined to a single nation's drawing board. This global tapestry of solar sail development is a powerful engine for innovation. Japan's triumph with IKAROS demonstrated that the technology was viable, but it was only the opening chapter. Across the Pacific, the United States has cultivated a unique public-private partnership. NASA advanced projects like NEA Scout work in parallel with the grassroots passion of the Planetary Society, whose LightSail missions proved that citizen-funded science could achieve orbital success. This diverse approach, blending institutional rigor with public enthusiasm, pushes the entire field forward at a remarkable pace. Europe has entered the arena with its own sophisticated designs. The European Space Agency has invested heavily in its Gossamer program, a series of technology demonstrators focused on one of the most difficult challenges, the flawless deployment of colossal, ultra-thin sails in space. Their work on intricate folding patterns and precision-controlled boom deployment is solving the practical problems that will allow us to build the city block-sized sails of tomorrow. Meanwhile, a new space power is rising. China has publicly declared its ambitions for solar sailing, outlining plans for missions that would use photon pressure for ambitious asteroid tours. They are even investigating a profoundly practical application, using sails as gentle, free tugboats to nudge dangerous space debris into orbits where it will safely burn up. This cleans up our orbital backyard while proving the technology. This international interest creates a fascinating dynamic. It is a race, but a deeply collaborative one. Each success by one nation raises the bar for all others, accelerating progress far faster than any single country could manage alone. This healthy competition naturally opens the door for partnership. Imagine a future mission where one country provides the launch vehicle, Another contributes the advanced sail membrane it has perfected, and a third supplies the suite of scientific instruments. This model of shared expertise and cost is likely the only way humanity will fund and execute its most daring voyages, such as a precursor mission to the very edge of our solar system. The race to harness light is a peaceful endeavor, uniting the world in a shared goal of sustainable exploration. This foundation of cooperation is not just beneficial, it is absolutely essential for the monumental task that comes next, building a permanent infrastructure throughout the inner solar system. The true power of solar sailing may lie not in exploration, but in construction. We can shift our perspective from viewing these craft as singular missions to seeing them as permanent fixtures, the trucks and tugboats of the inner solar system. Envision a future where reusable sail tugs are stationed in orbit, waiting for a call. A multi-billion-dollar telecommunications satellite begins to drift too low, its orbit decaying from the faint drag of the upper atmosphere. Instead of writing it off as a loss, a sail tug maneuvers alongside. Using nothing but the gentle, constant pressure of sunlight, it nudges the satellite for weeks or months, patiently pushing it back to its proper, stable altitude. This service could extend the life of our most vital orbital assets by years. At the end of a satellite's life, that same tug could guide it safely to a graveyard orbit, actively cleaning up the growing cloud of space debris. This transforms the solar sail from a disposable probe into a reusable, profitable asset, a workhorse that pays for itself many times over. The economic logic becomes even more compelling for supply lines. Consider the needs of a future lunar gateway or a base on Mars. They will require a constant, reliable stream of cargo, from spare parts to food and water. Solar sail-powered cargo vessels are the perfect solution for this slow but steady freight. Once a sail barge is launched from Earth, it could make endless loops between our planet and these outposts. It never needs to refuel. Its schedule is as predictable as the sunrise, creating a permanent, affordable logistics chain in space. This establishes a true in-space transportation network where moving between orbits becomes cheap and routine. It is the foundational infrastructure for a bustling cislunar economy, turning the void between worlds from a forbidding barrier into a well-traveled highway. This vision of sustainability, of building a spacefaring civilization that maintains and reuses its assets, is the ultimate promise of learning to sail on sunbeams. This silent, clean operation makes solar sailing one of the most environmentally conscious technologies we have ever conceived for space. While a roaring chemical rocket pours tons of combustion byproducts into the atmosphere, a solar sail slips into orbit with no exhaust, no smoke, and no emissions. Its engine is pure physics, not controlled explosions, even compared to nuclear-powered systems, which carry inherent radiological risks and complex safety protocols. The sail presents a completely clean profile. It harnesses a force that is perpetually renewed by the sun, leaving nothing in its wake but the faintest shadow. At the end of its long life, the only debris is the inert structure of the craft itself, a stark contrast to the scattered fragments and frozen fuel tanks left by conventional missions. This taps into a deeper, growing ethical imperative for our species. As we stand on the brink of becoming a true spacefaring civilization, one that may one day mine asteroids or build settlements on Mars, how we take our first steps matters immensely. Do we arrive with the same resource-intensive mentality that has so often scarred our own planet, or do we choose a wiser path? Solar sailing offers that wiser path. It demonstrates that we can explore and utilize the solar system not as reckless consumers, but as thoughtful stewards. The technology itself is a statement of principle, proving that humanity can harness the natural, abundant forces of the cosmos with elegance and respect. This is not merely a technical upgrade, it is a moral one. It sets a positive precedent for all that follows, ensuring that our expansion into the stars is built on a foundation of sustainability and responsibility, a legacy far more valuable than any single mineral we might extract from an asteroid. Carrying human beings on a sunbeam presents a challenge of almost unimaginable scale. The gentle push that so perfectly propels a tiny probe is a whisper against the immense mass of a ship designed to sustain life. For launching from Earth or any quick maneuver, the thrust is simply too faint. Yet the dream of human-crewed solar sails is not entirely lost to the stars. Imagine a future where vast, self-sustaining arcs voyage between established colonies on Mars and the asteroid belt. For these colossal vessels, a solar sail would not be the main engine, but a constant, silent partner. Its perpetual nudge would work alongside more powerful propulsion systems, gradually adding kilometers per second to the ship's velocity over the years of its journey. This slow but steady acceleration could shave months or even years off the transit time to the outer worlds, all without consuming a single gram of precious reaction mass. The sail itself would become a multi-purpose marvel for the crew. That immense mirror-like surface could double as the ship's primary power plant, a sprawling solar array catching endless energy from the sun. With the right materials, it could even be positioned to act as a shield, deflecting dangerous cosmic radiation and protecting the fragile humans inside. Beyond the physics and the engineering, the psychological impact of such a voyage would be profound. To live aboard a vessel pushed by the physical pressure of starlight is to feel a direct, tangible connection to the universe. Your journey is literally written in light. You are not just passing through the cosmos, you are engaged in a constant, silent dialogue with it. This transforms the ship from a mere machine into a true sailing vessel for the interplanetary age, evoking a romantic and serene form of travel that stands in stark contrast to the explosive power that first took us from Earth. While we will always need high-thrust systems to break orbit, solar sails could become the graceful, sustainable clipper ships carrying the cargo and colonists of tomorrow on their long, steady voyages between the worlds. This human connection adds a deeply inspiring dimension to the technology, a reminder that our future in space could be one of quiet harmony with the forces of nature, not just a battle against them. A solar sail is the ultimate rapid reaction force for the cosmos. Its unique potential lies in a powerful combination, the ability to be stored for years in a compact state, then unleashed on a trajectory no conventional rocket could afford to follow. Imagine the sudden discovery of a new comet, a pristine visitor from the outer solar system diving toward the sun. By the time we spot it, a traditional mission would take years to design, build, and launch, long after the comet has swung around the sun and vanished back into the dark. But a pre-positioned solar sailcraft, already built and waiting in orbit, could be commanded to set sail within days. Catching the light, it would spiral onto an intercept course, its gentle but constant acceleration allowing it to race alongside the mysterious object, analyzing its composition and structure during its brief, brilliant passage through the inner system. This transforms our entire approach from reactive to decisively proactive. The same principle applies to the most tantalizing targets of all, interstellar interlopers. When the strange, cigar-shaped object Oumuamua sped through our solar system, it was already on its way out by the time we noticed it. We had no way to catch it, and its secrets vanished with it into the void. A network of ready-to-launch sailcraft would change that forever. Upon detecting the next visitor from another star, we could dispatch a fleet of these agile scouts. Their fuel-free nature means they could adjust their course over long periods, matching velocity with the object for an extended, close-up study. Were it a fragment of an alien world, a dormant comet, or something even more exotic, we would finally have the means to know. This capability turns fleeting chance into guaranteed discovery. Having these silent sentinels on standby ensures we are never again caught unprepared by a surprise from the depths. It is the difference between glimpsing a strange ship on the horizon and being able to send out a boat to meet it. To build this future of cosmic first responders, we must inspire and empower the next generation of engineers and scientists who will design these missions. There is a special magic in an idea simple enough to sketch on a napkin yet profound enough to push a spacecraft between worlds. Solar sailing does more than revolutionize propulsion. It reignites a fundamental sense of wonder. That visceral image of a silver sail catching sunlight bridges the gap between childhood dreams and cutting-edge physics, making the cosmos feel accessible in a way a roaring rocket never could. This unique power to inspire is perhaps its most underestimated legacy. Grassroots projects have turned this vision into a global classroom. The Planetary Society's LightSail mission was not just a technological demonstrator. It was a community built on a Kickstarter campaign, funded by thousands of passionate supporters who wanted to see a piece of their own hope sail through the heavens. These backers did more than just donate. They became active participants, analyzing streams of image data from the spacecraft, spotting stars in the background, and sharing in the collective triumph of a successful flight. This model of open engagement democratizes discovery, transforming passive observers into a mission crew. That spirit of hands-on involvement is now spreading to university labs worldwide. Student-led teams are designing their own miniature solar sails as CubeSat projects, tackling the same real-world challenges of deployment, attitude control, and orbital mechanics that professional engineers face. For these students, a textbook equation about radiation pressure is no longer an abstract concept. It is the very force they must harness to keep their own creation alive in the void. This practical experience is priceless, forging the next generation of aerospace engineers, programmers, and mission specialists who will build the sustainable space economy of tomorrow. Beyond technical skills, solar sailing imparts a deeper, more human lesson in patience. In an era of instant updates and immediate results, these missions operate on a different timescale. A solar sail does not race from the launch pad. It embarks on a slow, graceful spiral, its speed building imperceptibly day by day. Following such a journey teaches us to think in terms of years, not seconds. It rewards long-range planning and steadfast perseverance, reminding us that some of humanity's greatest achievements are not sprints, but marathons. This cultural shift is as vital as any technological breakthrough. By making the grand endeavor of space exploration feel personal, participatory, and patiently beautiful, solar sailing helps cultivate a global culture that looks to the stars not with trepidation, but with ambition and a shared sense of ownership. It proves that the future of cosmic exploration is not just for governments and billionaires, but for students, teachers, and dreamers everywhere. Piece these roles together, and a breathtaking tapestry comes into view. The solar system transforms from a collection of isolated destinations into a single, interconnected domain, humming with silent activity. Picture a celestial internet, its nodes not made of wires and servers, but of specialized sailcraft, each performing a vital function. At its heart, near the sun, a network of weather monitors holds station, their vast sails angled to maintain a constant vigil on our star's tempestuous moods. Further out, a series of communication relays form a persistent data bridge between Earth, Mars, and the asteroid belt, their sails ensuring they never drift from their crucial positions. Docked at orbital ports, reusable tugs stand ready, their sole purpose to gently nudge expensive satellites back to their correct paths or to guide aging hardware to safe graveyard orbits. And scattered throughout this web, a constellation of rapid response scouts lies in wait, folded and dormant, until the moment a new comet is spotted or an interstellar visitor is detected, when they will unfurl and race to investigate. This is not a future of occasional, heroic missions. It is the birth of a permanent, scalable, and resilient infrastructure for an entire civilization. The economics become transformative. The initial cost of launching these sailcraft is quickly amortized over decades of fuel-free operation. Moving data, cargo, and even people between worlds shifts from a prohibitively expensive endeavor to a predictable, manageable expense. This infrastructure makes the entire solar system feel smaller and more accessible, not by shrinking the distances, but by mastering the medium between them. We evolve from being occasional visitors to becoming permanent residents of our cosmic neighborhood. The solar sail is the quiet, elegant enabler of this new age. It redefines exploration itself, moving beyond the paradigm of flags and footprints to one of continuous connection and deep understanding. This is a future built not on explosive power, but on graceful persistence, a testament to our ability to harness the universe's own gentle forces to build something lasting. The journey of a sunbeam, it turns out, leads not to a single destination, but to the weaving of an entire celestial community. From those first theoretical musings to the triumphant flights of LightSail 2 and IKAROS, this entire journey stands as a powerful testament to human ingenuity. It reflects our enduring, almost primal desire to push beyond the next horizon. We have traced the path from a fundamental quirk of physics, the momentum of a photon, to the audacious dream of reaching another star. Along the way, we have seen how this elegant technology shatters the economic barriers of spaceflight, enabling missions that were once pure fantasy and laying the groundwork for a permanent, sustainable infrastructure around our world and beyond. But solar sailing offers us something even greater than a new engine. It presents a new philosophy for cosmic exploration, one built on patience instead of haste, on elegance instead of brute force, and on a profound harmony with the natural forces of the universe. The visionary astronomer Carl Sagan, an early and passionate proponent, captured this spirit perfectly. He envisioned that such technologies would allow us to become true starfolk, sailors riding the very light that has always illuminated our way. That new age of cosmic exploration is no longer a distant dream. It is dawning right now, and it will be powered not by violent fire, but by the silent, endless push of light. The central question has fundamentally shifted. It is no longer a matter of if we will use solar sails, but a thrilling mystery of just how far they will ultimately take us. We would love to hear your thoughts on this incredible future in the comments below. And if you are ready for the next voyage into the frontiers of technology, be sure to subscribe so you do not miss a single journey.